atomic to molecular systems, how our potential changes. So, for molecular systems, what will be our total U? So, as I said that we have to okay, when you are talking about a molecular system, this is what I am talking about. So, previously our particles were just the atoms, but here now our particles or our systems are composed of molecules. I have this molecule, I have this molecule, I have several such molecules floating in the system. So, I am talking about now the total U for this system. So, each molecule is composed of 4 atoms as I have drawn here. So, therefore, this atom will interact with this atom will interact with this atom will interact with this atom will interact also with this atom, this one will also interact with this atom by pair potential. So, we have one of those inter particle pair potentials, one of them, let us say we take the Lennard-Jones. If we take the Lennard-Jones, so we have I less than j for epsilon ij, sigma ij divided by r ij to the power 12 minus sigma ij rij to the power 6. So, we have the short range potential if the particles for biological systems, particles also have their partial charges. Okay, I correct this one. Okay, instead of saying atomic charges, I would prefer to say partial charges. So, therefore, this plus you also have sum over I, sum over j, zi, zj by 4 pi epsilon 0 rij. So, these two are intermolecular interactions. Apart from this, we also have intramolecular interactions. We also have intramolecular interactions. And what are those intermolecular interactions? Because in the molecule, we have bonds. This particle is connected to this particle by a bond. This particle is connected to this particle by an angle, and this particle also connected to this particle by a dihedral angle. So, here in each of my molecule, I do have an angle here, I do have a bond between here and here, here and here, another bond, here and here, another bond. And each molecule also have angles. Here is one angle, here is another angle, and then I do have a dihedral composed of 4 atoms. So, these are the intramolecular interactions. So, for a molecular system, apart from the Lennard-Jones or Hertzsprung plus electrostatic, we also have the intramolecular interactions. So, what's the form of the intramolecular interactions that we need to incorporate in total U here? So, total U for a molecular system will composed of as I said, that it will have a bond potential, it will have a angle potential, it will have a dihedral potential, plus it will have a U short range plus U long range intermolecular plus intramolecular interactions. So, my total U of a molecule would be something like this, which we can expand as U bond. We can write as something like this. I sum over all bonds into the system, all bonds. This can be written as Ki by 2 by Hooke's law. Sorry, not R, not to confuse you, I would say Li minus Li, where this is the equilibrium bond length, and Ki is the force constant. So, this is overall bonds. Likewise, angle also we can express by Hooke's law. So, here I write K theta by 2, and I can express that as theta I minus how do I express here? Minus theta I 0 square. Here again this is the equilibrium angle. So, basically this term represents the bond stretching, how this bond basically stretches and compresses. So, this is the bond stretching contribution. This term represents the bending. The angle bending, plus you have the dihedral term. So, from here I come to dihedral, which we can write as sum over all dihedral So, this is one of the different forms for dihedral one can write. Of course, for angle also you have more sophisticated potential, but the potential based on Hooke's law also holds good for most of the systems. So for dihedral, the expression we can use is Vn by 2 1 plus cos n omega minus gamma. I'll explain each of these terms very soon. So this is dihedral. So therefore 1, 2, 3 they are the intramolecular, and then you have the intermolecular. So this I can put together. So this is the total potential of a molecular system, where you have the bond contribution due to all bonds in the system, you have the angle contribution from all the angles you have in the system, you have the dihedral contribution, and then you have intermolecular interactions which can be defined by short range Leonard Jones or one of the other potential I have introduced. And if your particles are having partial charges, then you also have the electrostatic potential. So this is the total U of a molecular system. Now let us look at what are the different terms we have in this dihedral potential. Which we have written as Vn by 2 1 plus cos n omega minus gamma. So what are the terms representing? So the first term Vn is called barrier height. Vn is called barrier height. Omega gamma is called the phase factor, and n is called the multiplicity. And here omega is basically the instantaneous value of the dihedral. Yes, one thing I should have mentioned you here is that, so this Li0 is the equilibrium bond length, whereas Li is the instantaneous value of the bond, which means that the bond is basically stretching and compressing. So Li0 is the equilibrium bond distance around which it is stretching and coming back, stretching and coming back. So this change in Li0, change in bond length, is basically the Li. So Li is the instantaneous value of the bond length, and Li0 is the equilibrium bond distance. Likewise here, theta I is basically the instantaneous angle between particle I, j and k. atom ij and k, and theta I0 is the equilibrium angle between those three atoms. Here also the omega is basically the instantaneous value of the dihedral. So what is dihedral? Dihedral is basically you have particle 1, 2, 3 and 4. So this angle is called the dihedral angle, so which you can basically rotate from 0 to 360 degree, and how in the process of this 1, 2, 3 and 4, how the energy is changing from 0 till 180 till 360. So that's a dihedral potential, and that is the definition of dihedral angle. So how the definition of these three terms will be clear to you if I draw the U dihedral of let's say I'll draw for a single carbon-carbon bond. Okay. So if I draw this, let's say, so this is my 180. So this is my 0, 60 degree, 120, 180, 240, 300 and 360. So basically I have this single, so with respect to this bond, I am basically rotating these 4 atoms and how the energy is changing. And in x-axis, this is my 0, this is -1, this is 1, this is 2, this is 3 and so on. So the nature of this rotation, dihedral is also called the torsional angle. So this should look something like this. Might reduce this one little. Oops. Oops. Okay. Let me draw it a little better. Okay, so I just need to change my so this is 180, this is 60, 0, I'm sorry, it is not exactly this would be 240, this is 300, and this is 360. Okay. So what is N? What is Vn? So Vn is barrier height. So here, okay. So if this is my 2, and so here Vn is the barrier height, which is the maximum energy. The rotation has to cross. So the barrier, basically, the highest energy is here 2.5. So Vn is the barrier height, which is 2.5 kilocalorie per mole. Gamma is the phase factor, which tells the angle at which the energy was the least. So here my gamma is 180 degree, because this is the angle at which the energy is the least. And N is the multiplicity, which is basically the number of minima in the whole rotation. So here I have 1 minima, 2 minima, and 3 minima, so N is 3. So this is the dihedral potential, and this is a intramolecular property what one has to include to make the model of a molecular system.